All right, so before we get into the last topic of phase 2, some questions to answer. So first question I got from Melody was, when you do like log transforms of, your independent or dependent variables, what are you doing there, and like how do you make sense of that? So the whole idea of linear regression and how you get linear regression to work best is if you have strong linear relationships between your dependent variable and all your other independent variables. So the purpose of doing a log transform is to get a better linear relationship between your independent and dependent variables. And this can happen, you can transform any of your variables. You can transform like your price, which is your target variable, or you can transform like your continuous independent variables. Only makes sense to transform continuous ones. So there are no restrictions on what you can or cannot transform as long as they're continuous. But the hard part becomes, since you have like a logged variable, the interpretation gets a little bit tough. Let me see, I think this is an example. So this again is our that car data frame with the predicting miles per gallon. I don't know why I keep using this because I don't know anything about cars, but as you can see here, acceleration, acceleration was logged and then scaled. So let's talk, they're all logged and scaled. All right, perfect. So we can talk about it like that. So I believe miles per gallon was not scaled. So here with these coefficients, and these are scaled variables, by the way, having this coefficient of -0.02 means that for every 1 unit increase in the log scaled acceleration, miles per gallon will go down by 0.02. So when you're doing that, when you make that interpretation, saying that the acceleration is not straight up acceleration, but instead it's log scaled acceleration, and you have to first find out what is 1 unit of log scaled acceleration equivalent to in terms of like actual acceleration. And that that includes the process of you working backwards. So you would have to, depending on what you did first, and in this case, they actually did they didn't log acceleration. So let's talk about this. Let's pretend we're talking about displacement. So they logged displacement and then they took the z-scores. So to get it back to actual displacement, whatever you have here, you would have to unscale it. So multiply it by its square root, multiply it by its standard deviation, and then plus back the mean, and then unlog it. And the opposite of log is an exponent. I will say that part is not the important part, like getting the like actual values. I will say it will make your model for your project much more interpretable since you have those like actual values. But another way that you can interpret log transforms is I have linked this at the bottom of our resources on our project guidelines. But this resource basically tells us a different way of interpreting log coefficient. That basically does it for you in terms of percentage change. And percentage change helps as well. It gets a little bit more complicated as well if you do log and then scale, or scale and then log. So just keep in mind if you do that. So this basically tells you like what you're logging and what you're not logging, and then based on that, how you interpret. So for example, if you had logged one of your independent variables, but you didn't log your dependent variable, you would say if we increase x by 1%, it increases by coefficient over 100 units of y. So in this case, let's say this was your square foot. You had log square foot, but you have your price here. So you're saying, all right, if I increase my square footage by 1%, y will increase by whatever the coefficient is divided by 100 units. And then all the same for if you logged your dependent but not your independent, and then also if you log both. So I'm okay if you don't unlog and use these instead. Where the unlogging actually does come in is with the, sometimes that might affect your mean squared error, especially if you had logged your dependent variable. So if you logged your dependent variable and you can't figure out how to unlog it, I will say that is not something that you'll get penalized for. If you can't figure out the right way to unlog it, you will still get some values. The values, I'm guessing, will just end up being a lot smaller. And then that, I do think it's fine for us to work through during our project reviews or ask each other questions. One thing to remember, and I'm not sure if I have a good example here. Let me use an example from our other notebook, which hopefully I still have open. Let's see. There we go. So here, I hope I looked at RMSE at some point. Did I not? Okay, so here, I'm taking the mean squared error of my y train and y hat train. If I have log transformed my y variable, remember that before you take the mean squared error, you actually have to unlog it first. So you would unlog your y train and y hat train first, and then calculate your mean squared error, instead of taking the unlogged of this. Got it? If that part is not clear right now, that's not the important part of the project. If it's something to do with like untransforming, because we will actually look at better ways to do that next phase, I don't really care if you like unlog or untransform your variables, like not in the right order. Usually you can tell if your numbers are just, they don't seem right. But yeah, any other questions about that, like how you interpret transformed variables?
I think I was trying to figure out like why you would log, or what would prompt me to log my dependent variable.
Yeah, okay.
I get the independent ones because I know we looked at graphs and decided
Absolutely.
logging them made them more normal, but why?
Yeah, so actually something like this might be, I feel like something like this might be a good thing to actually log your independent variable, because you can sort of see here with these, especially with these three variables here, you can see that instead of a line, something that looks like it could fit better would be like a curve like this. And once you see like a slight curved relationship, logging usually helps with that. If instead of having it curved like this, it might actually make it a little bit more linear. And also like logging helps to reduce the distance of your outliers. So if like, let's say, let me think of a way that I can show this. Maybe there's a diagram down here that has, because I talked about transforming here. So for example, with displacement, your outliers here are like further out. After you log transform it, your outliers sort of like come closer. So if you have like a variable with a lot of outliers, like in terms of, for this project, I know for price, you do have quite a few, they're not so much outliers because they're not like one-off instances, but you do have like a longer tail if you were to look at the histogram of your price. And so by log transforming, you sort of like narrow the distance of your outliers, if that makes sense. So because log does change the distribution in that way, it might give you a better linear relationship if you were to log your price. It gives you a better relationship between, like, you get a better relationship basically with your log price and your other variables, if that makes sense. Because the whole idea of making all of these transformations, which is also actually related to what we're going to be talking about today, in the subtopic 20, is you're trying to get the best linear relationship between your dependent and independent variables, and just doing transformations help with that. So yeah, typically logs will, on the tail end, on the higher end, squeeze in your outliers. But also, I think something else that log transform helps do is if you have a lot of points that are like compressed at the low end, it helps to spread that out as well. So the effect is that your overall distribution, as you can see here, displacement, before it's logged, it was like a really tall bar at the very start. After logging, it's sort of like kind of evened out. So logging has that effect on a variable. And if anyone's curious mathematically, which I mean, this is not super important to know, but it's because the log graph has this shape. And if I'm not wrong, I believe this is 1, but I don't remember. Yeah, I think it's 1. But basically on the low end, if you have like, this is x and this is log of x. So, oops, yeah. So if you want to compare like values that are like from here to here, for example, from 1 to this point, the distance between 1 to this point will be spread out a little bit more. So this is what I mean by on the low end. And on the high end, so let's say we have, oops, let me just use a line. If I have like this point here, and let's use this point here, which is, this is an estimation, but these distances horizontally are roughly the same. But if we look at it on the log axis, this gets squeezed smaller. So it's because of that nature of the log transformation that it usually smooths out your data a little better. This is also something that you can plot like to see if a log transformation will work better or not. What you can do is log transform your variables and literally just look at the scatter plot again. And sometimes you might see like a better linear relationship. All right, anything else about that? Okay, so the next thing, Matthew had a couple questions on what happens if you have a high p-value and y-intercept, and also like what are the implications of dropping your dummy variables on that, and also unit vector transformation. So a high p-value y-intercept, and I did send out a reading yesterday, but it, I guess, didn't really address this directly. If you do see a high p-value for intercept, something that we didn't really talk about was like, what exactly is the hypothesis that's being tested for the intercept? Because your intercept could be 0, and that still determines like the overall relationship. So the way that, based on what I've been reading, because this is not really explicitly stated anywhere, having a high p-value for this intercept means that this coefficient is likely to have happened by random chance. So I feel like for me, it's easier to think of it as like not like a 0 versus 46, but rather just like, is 46 random, or are we certain about that number? So if you have a high value for intercept, usually it has something to do with the rest of your variables not fitting well either. So I feel like you'll be very unlikely to have like all 0 p-values here and then a high intercept p-value there, but not 100% sure on that. When you drop dummy variables, or like in the case where you had your drop first equals to true, when you're dropping a dummy variable, you're not exactly saying that that coefficient is, I mean, you kind of are saying that that coefficient is part of the intercept, but once you've dropped the dummy variable, so like in this case, you have all the other years that we have ended up dropping, I think, in this case, right? I think we went from like 70, we had all the 70s and I think all the like some 80s as well, but we've dropped it down to 2. Included in the intercept, and I think what's important to think about, something that's important to remember here is we're talking about like relative cases. We're talking about relative cars here. So even though, yes, in the intercept, we have information about all the cars in the 70s and maybe like 81, 83, 84, 85, that information is not taken into account when fitting your model. So when you're fitting this model, and also one reason why, the more categorical variables you have, you tend to have like a higher R-squared, or the more variables you have, you tend to have a higher R-squared, is that you're increasing the number of dimensions that you're looking at it. So here, if we're only looking at 80 and 82, in total we have 5 dimensions of data that we're fitting our line across. If we had not dropped like the years 70 to 79, we would be looking at 15 dimensions of data. So I guess the significance of the dropped variables, yes, it is partially taken into account in the intercept, but more importantly, the variables that are left, we're looking at whether something is made in the year 80 or not in the year 80, whether something is made in the year 82 or not in the year 82. So what goes to say is that, let me see, how can I summarize this? Like, if your dropped variable, if you're dropped, let's say you made a bunch of dummies and like all of the other dummy variables for a year had high p-values, those insignificances are not brought over into the intercept, because the intercept is actually fit on these 5, it's refit on these 5 dimensions rather than on those 15 dimensions, if that makes sense. It's a little bit abstract, but I hope that helped. Okay, I don't know, Matthew, you have any comments on that? But yeah, basically, if you're dropping, you don't have to be very wary of high p-values affecting your intercept if they're being dropped, because you're basically refitting your line in fewer dimensions. Yeah, I think that's, yeah, all right. Glad to see that helped. All right, well, if there are any more questions that are not related to topic 20, we can talk about them after we go to topic 20's materials. I don't think I'm forgetting anything else, because that's all I wrote down. Oh, unit vector transformation, sorry. With the unit vector transformation, there is no built-in formula for that. And the idea of using a unit vector transformation is actually a way of reducing the number of features that you have. So unit vector transformation, first of all, you don't want to do that on like a set of dummy variables. And I'll sort of explain what that means. So let's see if this works. Let me take a look at what data was. Let me rerun this real quick. Let's actually do it on, let's hope that this runs. I had an issue running this notebook earlier. Okay, great. Let's try a unit vector transformation here. Unit vector transformation basically, for example, takes a bunch of your continuous columns and kind of combines them into one column. So we can do that on any number of columns. So let's just, for example, maybe do a unit vector transformation of displacement, horsepower, and weight. So let me try this. I haven't done this in a while, but let's try doing this. So unit car displacement, and I think you have to square it, plus car df horsepower, again square this, plus car df, I'm just going to do these 3 for now. Wait, 2. Hopefully this comes out nicely. All right, and I believe what you also have to do is take this entire thing and square root it, 0.5. And then I think you have to also divide it by the magnitude of this, but dividing it is fine, same formula, just apply the formula. And with unit vector transformation, basically this number, I mean, after you divide it by, I want to say you have to divide it by the length of this vector, which honestly, there are, we'll actually get into this in a later topic, but this number here is basically a lower dimension representation of these 3 these 3 columns. I personally don't think for this project this transformation would be helpful, unless you think that, you know, this combination or this way of looking at your features does have a linear relationship with your target variable. I would say it would be harder to justify why do this kind of transformation. Honestly, perhaps, sorry, I'm just like thinking out loud here, because you do have like a couple different square foot measurements or features, like you have your square foot living, lot, basement, whatever. Actually, you can maybe do something like this, because it kind of in some way takes a good average. Oh, I see. Matthew says that using it to deal with multicollinear. Actually, yeah, that's it. Yeah, that's actually kind of what I was thinking as well, because you have like those square foot variables that are all collinear with each other. It's a way of, yeah, you're absolutely right. It is a way of, you know, incorporating all of these variables while not having this be multicollinear or correlated with another variable in your model. So yeah, if you're thinking about using it that way, that's a good idea. If anyone's really interested, there is actually a better way to do this, in my opinion. It's a method called principal component analysis. which will actually reduce your feature space in a way that mathematically makes more sense. Because this way, wait, where was it? This way of doing this, it does, it kind of doesn't really consider the relative importance of each of these. So I'll send this out. Let me see, scikit-learn PCA. PCA is something that unfortunately only comes in at the start of phase 4, but the implementation is kind of the same. Basically what you do is with this, you can tell it how many features you want to reduce it to. So for example, if you had like 5 features that are correlated with each other, 5 features that are correlated with each other, and you want to get it down to 1, you can really just tell it 1. And then it will basically give you 1 feature, and each 1 feature is a linear combination of those 5 features. But yeah, I think normalizing them first will help as well. But yeah, that's actually a really interesting thought. I didn't really think about doing the unit vector transformation for this purpose, but it makes a lot of sense. Yeah. Thanks, Matthew.
That would let you drop those variables that you use to make the vector?
Yes, yes, that will allow you to drop those variables that you use to make the vector. I'll send this out later as well. We will get more into like what this is used for. This is actually a method it is a known method to reduce the number of features that you have. And then basically you'll get like a smaller number of features, and they're all like a linear combination of each other. And also I think by default, they won't be correlated with each other if, let's say, you reduce it to like more than 1 component. So yeah, we'll talk about mathematically how this works in phase 4. But if anyone's like curious about it, the implementation of this is the way that the syntax works is the same as the scikit-learn linear regression, where I'm not sure if they have an example here, but you instantiate it first, and then you fit your PCA, and then you'll be able to get your new variables. It does make it much harder to interpret, though, I will say. But yeah, same with unit vector. Anything that you're reducing dimensionality of, you do lose a lot of interpretability, and there's a lot more work to be done in untransforming them. But yeah, that's a really, really awesome thought. I really appreciate that.
Ish, based on what you calculated earlier, and also the unit vector formula, each value in each feature will be divided by this number?
Yeah, so this is I believe it's the numerator. So what I did was the numerator, okay, just kidding. So this is the denominator. So I'll just have to take each x divided by that. So I believe if we go back to this, the correct way of doing it, because I wasn't referring to the formula. The correct way to do it would be if I want to make a new one, and let's say I wanted to do it in terms of, let's say I wanted to do it in terms of displacement or something. There we go. All the numbers will range between, and I think if I do a histogram, not sure if it'll let me stack so many things. All right. But anyways, you'll get this series, and then you basically will have this number, and this number should range between 0 and 1. Yeah. Sorry, Ali, I forgot if you had another part of your question.
Okay, thank you.
All right. You're welcome. Anything else? Cool. Let's talk about these things real quick. So in topic 20, they did talk about the bias variance trade-off. And I think that also ties into cross-validation. So I'll talk about that first. Then we'll talk about interaction variables and then polynomial regression. So first off, cross-validation is something that I mentioned quite briefly in the last study group, but cross-validation is basically another layer of train test split. I like to think of it as another layer of train test split that typically is done on your train set. I would be careful. I think one of the labs does have an error, and a couple people did point out to me that I think the cross-validation lab, there is an error, and you'll see like all the errors have the same value. And that's because I think they're using the wrong variable. But if you just like replace it with the correct one, you should see something like this. The idea of doing cross-validation is just making sure that your model isn't overfitting to a certain part of your data. So how cross-validation works is after you train your model, and this is hard-coded cross-validation, but instead we're going to look at here. With cross-validation, when you train your model, they're actually going to fit your model onto different subsets of your, data to just make sure it's not overfitting anywhere. Typically, cross-validation for something like linear regression wouldn't give you any crazy results because of like, we're doing train test split and the splits are quite random, and the processes in how linear regression is solved is pretty standard. This will actually come way more into play when we take a look at less interpretable models. So for example, doing cross-validation is very, very important for things like neural networks, because neural networks are essentially black box models. If you were to like train a neural network with the same feature set like 3 times, you're going to end up with 3 very different models just because it's a black box. And that's why cross-validation becomes very, very important, because you want to make sure that, across your 3 different models, maybe you might want to pick one of them to be your final model. And that's why cross-validation is way more important in those contexts. But for this, it's just another layer of chain test split to just make sure that your data isn't being, or your model isn't being overfit to something in your chain set. Like, for example, let's just say that by some weird act of randomness, all of your outliers happen to be in your chain set. And then when you fit your model, you are like training your model and editing your model with all of these outliers in mind. And having some outliers are good, but like, having too many outliers in your chain set, and for example, no outliers in your test set, can lead to some like weird things in your model. Like your model would have learned information about outliers that you might not want to take into consideration. So to do that, basically the idea of cross-validation is you choose a number. Usually it's not a big number. I would say like no more than 20. But what cross-validation do is it basically takes your data set, and typically is your train set, and divides it into that number of parts just randomly. And what it'll do is it will run your model on each part separately and produce different error values. So in this case, you can see I plugged in my linear regression model, my X, my Y, gave it how many divisions I want. And then on each of those divisions, it gave me a negative mean squared error value. I don't know why it's negative. That's just how it is. So you can just unnegative it, or unnegative it, and then take the square root, and then you'll see if there are any subsets that have higher errors or like strangely higher errors. So something like this, negative 28, might be a little bit alarming. Of course, you would have to square root it and then take a look at this in context. Like for miles per gallon, square root of 28 will be about like 5. I don't know if like 5 is going to be, is that a big deal in context of cars? If it is, double check and make sure that in that specific split, you don't have any crazy outliers, because like a single outlier could pull your error up. But also, yeah, if 5 miles per gallon is not a big deal, then that's fine. So that's the whole idea of cross-validation. This code here is to show that with different chain test splits and training your model, you can end up with quite different training and testing errors. So which is why it's important to do this cross-validation, just to make sure that your errors are fairly even across different subsets of your data. Questions about this? All right, so that's cross-validation. I would say for this project, it makes the most sense to maybe throw in cross-validation and run it on your train set, so on your X train, Y train, and do it on like maybe your final model, just to make sure that your final model, it isn't like over-learning things that you don't want it to learn. All right, so the next part is the bias variance trade-off, and it's a very conceptual thing, kind of conceptual, but it's also very important to take into consideration. So the bias variance trade-off is basically the balance between underfitting and overfitting. We talked a little bit about overfitting when we are comparing our RMSEs. So if you have a very, very low error value in your training set, but your test set has a high error value, it means that it has overlearned some things in your training set that makes your model unable to generalize to unseen data. Typically, it's a trade-off. So if you were to un-overfit your model, like for example, maybe perhaps using less features, you are going to end up with a slightly lower you're going to end up with a slightly higher train error. But then what we're looking for is for our train and test errors to be around the same level, around the same magnitude. So just really quickly going over some definitions. Bias is underfitting, and it basically happens when a model cannot learn the training data, or it can't nor can it generalize to new data. So underfitting is, let's say, in your price model for your housing prices, you're only using like the number of bedrooms. And if you're only using the number of bedrooms to predict price, because the number of bedrooms as an input, you can only put, like, for example, like numbers from like 1 to 10, your predictions are not going to be as granular because you're not considering other factors. So that's underfitting. So yeah, wrong assumptions are made, you're missing interaction effects or didn't catch certain relationships. And so your algorithm will miss relevant relationships between predictors and target variables. So underfitting. So in contrast, overfitting, which is variance, happens when the model learns the training data too well, so it cannot generalize to new data. So here, it's when your model is too sensitive to small fluctuations in the training set. When variance is high, random noise in the training data is modeled rather than intended output, so it's overfit. One thing to be careful about with our projects for overfitting is usually when you have a very high R-squared, because an R-squared is a measure of how well your model fits your data. If you have a high R-squared, you tend to have you tend to more likely overfit your model. So that's why if you have a higher R-squared, I mean, that's great. It looks good to have a higher R-squared, but do check your RMSE and make sure that your train and test RMSEs are around the same magnitude. If you can have a high R-squared and maintain good RMSE values for your train and test set, that's great. But typically, you might want to sacrifice some of your R-squared to get less overfitting. Questions about that? All right, well, bias variance trade-off is also a common interview question. I have gotten some requests, actually multiple people have asked to, like, whenever I mention like, this is a common interview question, to like have a resource consolidating all of that. So I don't know if anyone has started doing that. If anyone has started doing that, let me know. But I'm also gonna spend some time putting all of that together, just so I mean, for myself, that I have a record of all these things that I'm saying as well. But yeah. Bias variance trade-off, it's more of like a conceptual thing and something to always keep in mind when you're training models. We will look at bias variance trade-off a lot more next phase as well. All right, so to move on to interactions and polynomial regression, these two are very, very similar, and they're basically ways to increase your feature set and basically test out relationships in your data that are less obvious. Basically, in a very similar way as doing like your log transform, you're looking for different relationships or different ways to get a linear relationship between your dependent and independent variables. And these are just different ways to try and find that. So interactions, in short, are just ways to get, it's basically multiplying different variables together. So we'll take a quick look at these examples. And this actually goes through a more like, I will say a more like scientific way of looking at interactions. So I'll go through this fairly quickly. So first we have our car data frame, and we're gonna use this final like tuned data set with these features. What they're doing here is we're first gonna split up our model year variable into older cars and younger cars. Basically what we're trying to do here is we're trying to see if there is an interaction effect between the age of a car as well as horsepower. So this is our hypothesis that we're testing here. We're just trying to see if, all right, maybe there's an interaction effect between our age of car and horsepower that might be useful to use in our linear regression model. And later, I will also briefly talk about a way to brute force this and just do it all at once. So if you already have a hunch of like what interactions would be good in your model, this is something to confirm that. So let me see, I think the plot will be there. Okay, so let's start with this one. What we're doing here is we are running two separate single variable regressions. So what's happening here, you can see that I've instantiated two separate regressions. First I have horsepower 1 and horsepower 2. And then I have, and I'm basically fitting two separate regressions, basically one for the younger cars and one for the older cars. Now, with this regression here, the coefficient, as you remember, is the slope between horsepower and the age of your car. And basically these coefficients look to be quite different. So regression 1, which is the older cars, regression 1 has a relationship of not as negative as younger cars. So you can sort of also think of it as like, maybe I want to segment my data, and maybe there's like a certain linear relationship on like one part of my data and a different linear relationship in another part of my data. And that's also one way that you can do interactive variables. So basically, this is what this looks like. This is the miles per gallon. This is horsepower. And then these are the regression lines for the blue one is older cars. The red one is younger cars. If you plot this graph and you notice that usually you're looking for if your lines intersect. If your lines intersect is a good sign of them being different enough, because if your slopes are different enough, they will intersect. If they're not very different, they won't intersect. If they're different enough, is a good sign that maybe you want to try out an interaction variable. So what we're doing here, and let me see what we're doing over here. First, we're starting with a baseline, and we're just going to start with this baseline of 0.83 r squared. What we're going to do here is we are going to make an interaction variable that multiplies our horsepower with the model year and take a look at what the r squared is. So we can see a slight increase in r squared, which is good. And actually a 2%, and it's actually 2.7% increase in r squared. It's a pretty good thing. And then if we just add that interaction variable, you can see here our horse year happens to be a pretty significant variable in this model. So this is like if you have an educated guess on what interacts well with something else, this is the way to do it. Basically, something else to consider is after you've made your interaction variable, do you want to drop your original ones? Sometimes it actually works out that having both in your model works just as fine. If, for example, you have your interaction term, and if your model year and horsepower variables become insignificant, and basically leads to redundancy, you might see p-values creep up, and then that's something that you just adjust for after the fact. Questions on this so far? All right, so the one I wanted to show you guys, and I think it is actually also in the lessons. You have this library, this method called polynomial features. So this is another thing that you can try in your projects. If you have no idea what features will interact together, polynomial features allows you to interact everything with everything else. And so it's a very like brute force way of doing it, but this polynomial features basically transforms your data set to include all features. So let me actually see if I can code this live. Hopefully this goes well. But let's start with our car data frame. I think that's the easiest one to start with. Maybe, no, let's start with X. Let's do this here. Let me just make sure X is what I want it to be. All right. And we use our polynomial features. And as per here, what you do first, similar to what we were doing with the circular linear regression, you first have to instantiate your model, the tool that you're going to use. And we do that by first instantiating polynomial features. Having the 2 there actually tells you like how many degrees you want to multiply things together. So if you have 2 here, it'll just multiply like pairs of features together. If you do 3, it'll multiply trios of your features together, which, as you can see, will like the number of variables you'll end up in your data frame will go up by more than exponential amount. So once you have polynomial features 2, you can transform your data frame X. And just in case, I'm just going to copy and paste this over here. Paste this here. If I fit transform my X, and let's actually do like, I'm just going to call it X poly. And then let's actually take a look at what X poly looks like. It might take a while to run, so I hope not too long. There we go. X poly is an array. Okay, so we have this, and then what we can do is we can pd.dataframe this array. There we go. So you can see that we went from like all of just these features. What this table includes is every feature multiplied with every other feature, as well as every feature squared, multiplied by itself. There is a way to get the column names. I believe that that column names code is, if it's not here, it is definitely in your lessons. Let me see if they have the get the names. I don't want to spend too much time on this as well. Here, get feature names. Let me see if this works. Let's see if this works. Ah, here we go. So this will get your feature names. And basically this will be X0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, and 6. There's a way to like, there's a way to just edit the string such that it reflects the original names. But basically all of these are the column names for this. So actually I can really, really quickly do columns equals to this. And actually input features, let me just do, I think I can do x.columns. Fingers crossed. There we go. So you can see here, there's always a constant term because they always want to do by 0. They keep the originals here. And then you can see here, this acceleration squared, acceleration multiplied by displacement, weight squares, weight by everything else. So if you have all of these features, a brute force way to go about this is to take this and throw it into one of the feature selection methods that are outlined in your labs. In one of the labs, they outline some automatic feature selection tools like stepwise selection or recursive feature elimination. Take all of these, throw it into there, and just see what comes up. That's a really quick and easy way to cut down the number of features, but also include some interactions. Questions about this? All right, I mean, through that feature elimination stage, you can maybe find out what are some interesting relationships that you might not have thought of to begin with. So yeah.
For when you're doing the feature elimination, like I think it was the like recursive feature elimination, is there a good amount of features? You have to input how many features you want to keep, like which are the top features? Is there like a way you can do that logically, or are you just kind of guessing as to how many features you want to keep?
There are ways that I've seen like tuning the number of features that works best. Something interesting that I've seen being done is actually trying different numbers, and with the different number of features, so naturally, the more features you have, the higher your R squared is naturally, right? So something that you could do, and I will say, like, I don't expect many groups to do this because it's pretty, it's kind of a lot, but imagine here you have, and let me just draw this. So this is basically like number of features. And then this, for example, can be your R squared. So typically you're going to see a graph that maybe looks like something like this. It shouldn't curve down. Maybe it will, I don't know. But this would be a graph that you could plot. Like, for example, you're testing like maybe 10 features, maybe like 50, 100, I don't know, depending on how many you start with. Basically, you want to get it to a point before it plateaus. Because once it plateaus, the marginal increase in R squared that each feature brings you is going to be not that much. And recursive feature elimination basically will cut off, they'll like sort all your p-values and then cut off. So you can try like different numbers and just see like, all right, where is the point where each additional feature doesn't add much to my model? And that's something that you can do. This is a more like scientific way of doing it for sure. But honestly, for this project, I'm okay with if you just use some like arbitrary numbers to figure that out.
Okay, and then you would just do this with like your training data then?
Mm-hmm. Yep, that's right. Yeah. You can also not only look at R squared, honestly, to like contrast that, not contrast, but you can, instead of R squared, maybe look at a different color. Maybe you can also look at RMSE. Is that something that you want to optimize for? So instead of RMSE, so RMSE is actually going to start high and then get lower. And I expect that at some point it will like also start to plateau off. So also looking at it in that way could be helpful too. So yeah, any other questions about the polynomial features and like interactions? It's just a way to just check for relationships that are not immediately obvious. Of course, if you have other like hypotheses, like for example, you think, you know, maybe the ratio of your weight to cylinders is important, you can do that as well. Those are also relationships that you can incorporate. The next section that your lessons talk about is polynomial regression, and it's very much the same concept as what we were talking about with interaction features. Basically, if you know a feature by itself doesn't have a linear relationship with your target, maybe the polynomial transform does. Let me just, fingers crossed I have this data set. I knew it, that data set was not there. Give me a second. Let me just drag this data set back out. I always move it. Copy, paste. All right. So here we have this really small, simple data set just to like show polynomial regression. But let's say we're trying to predict yield. And honestly, I don't even know what yield is in this data set using temperature. And you have a scatter plot that kind of looks like this. And if you were to just fit a regular regression, let's take a look at what it looks like. If we fit a regression, obviously the line doesn't fit very well. It's going to try its best to fit a straight line through to minimize, you know, RMSE or your RMSE there, and you're going to end up with a pretty bad error. I think here your overall error is 0.37, which on this scale is roughly still about like a 10% error. And then your R squared is only 8%. As you can see, pretty obvious. You have a lot of points that are not even close to where the line is. Again, with polynomial features and like the square features, as we saw previously here, by doing polynomial features transforming, you actually do take into account polynomial features as well. So it's like killing two birds with one stone here. But let's say you already have an inkling based on like the scatter plots that you plot that, all right, I sort of see like a curve relationship here. It does take a little bit of like mathematical knowledge to know that a curve like this usually means like you're looking for a squared relationship. That part, which is why I'm pretty okay with people just brute forcing this part. But anyways, if you have the contextual knowledge that, all right, this looks like you have like a squared relationship there, what you can do is try the squared relationship. So all I'm doing here is adding a new column called temperature squared, adding it to our X. You can see here I have temperature and temperature squared. And here what I'm actually doing is I'm fitting it to both temperature and temperature squared because maybe there is a relationship with them both together. With that, you can sort of see that this regression line is predicting something that looks like this, which is pretty cool. And then if we just print our metrics, you can see that our mean squared error has gone down from almost 0.4 to 0.2. So we've halved our mean squared error. And then our R squared is a lot better. It is now at about 0.7.
Ish, when you're doing these things, would you want to have like logged and scaled your data before doing polynomial transforms?
For polynomial transforms, I will say that's a good point. because of different features having different magnitudes, I do think it's probably better to scale your data first.
Okay.
But it's also something that you can test out, seeing that if you scale and then polynomial transform versus polynomial transform then scale, what the differences are. I will say maybe, because if you don't scale, let's say you have like something like, let me scroll up and see what kind of information we have here. So let's say we have stuff like, where's our raw data? That's a little bit easier to read. I'm just gonna use this for now. So let's say we have like weight that is a big number, and then like acceleration that's a fairly small number. I think when you take the product of the two, I think you're accounting for a little bit more of the weight relationship than the acceleration relationship. So yeah, normalizing first will even it out. But sometimes having that like slightly weighted product, like by weighted, I mean like maybe you do want to consider weight a little bit more than acceleration. Sometimes that could also lead to a better relationship. So it's hard to say, but I do think like normalizing first does make sense. But yeah, these techniques of like doing interactions and polynomial regressions are just expanding your possible feature space to include like these combination of variables that will basically give you more to play with in tuning a linear regression model on top of just dropping p-values and getting rid of like collinear features. So yeah, that's pretty much it. I will say that like for these like interactions and polynomial regression, you don't have to include it in your project. If you want to, that'd be great, but it's not necessary to. I think the main thing that I'm going to be looking out for is just, are you doing the iterative modeling process? Are you able to make changes to your feature set or to your model and be able to interpret and see what those changes have done for your model? That's more of like the what I'm looking for in terms of like exactly what changes you're making. It's less important. It's just like, are you able to interpret how your model is changing with different iterations? Cool. Well, does anyone have any other questions? I know this is our last study group before I am gone for a couple weeks. So yeah, now's the last chance to ask me questions. I will say, if you do come up with any questions, perhaps like over the weekend, if you're working on the project with your project partner, if you come up with questions, this is a really good place to leave them all, especially if they're not like time sensitive questions, because this document will be what all the other instructors will be referring to as they cover these sessions. Cool.
Can I ask one question?
Absolutely.
In regards to the mini project, would we be able to just submit like if we didn't do it yet, I'm saying like I didn't do it yet, but would be able to submit like a link just like to the repo?
Yeah, whatever works for you. I really don't care what format you send it to me in, as long as I can open it and read it.
And it should be all in one notebook, you said?
Honestly, not necessary. If you feel like there's a lot of work to be done, let's say you each did like things separately and it's a lot of work to consolidate, honestly, it's fine. What I want to make sure is that you're getting like the main like foundational parts of running a regression down. And as long as you have that, other comments I will just send to you in your group.
Okay, thank you.
Yeah, that's really just making sure that you know how to interpret certain things, and also do you know how to run a regression and what you're actually doing. So I am still working through a bunch of these notebooks. I will get you these comments by end of the day.
Thank you.
You're welcome. Anything else? Cool. Well, again, really want to emphasize, if you have questions, do leave them here. It's really it makes the most sense, or post them on Slack, and you can either get each other's input or get DS support squad's input. Let me just make sure I have nothing else to say. Ooh, one final thing. Because a lot of you, so last time when I did the project groupings, I actually grouped you all by like what operating system you're using. So because now there's a higher probability that like some of you are paired with like one person on Mac, one person on PC, really be careful about your file names. So I've seen multiple instances in which when you have a Jupyter notebook with spaces in the file name. So specifically, if you have a space in your file name, which is actually very common, I noticed in the last project. If you have spaces in your file name, for some reason, there's a higher chance that your notebook might get corrupted, especially when you're sharing them across different OSs. So, I mean, it's also a good practice to not have spaces in your file names. So just wanted to warn you guys about that. I mean, the notebook does get corrupted, but there is a way to uncorrupt it, but I'd rather not go through those processes because it does involve like loading up a backup. All right. Well, I don't have anything else to share with you. We are officially done with the material for phase 2. So that means we're like halfway through the program, which is crazy. Let me stop this recording and then we can get into our feelings as usual.